cross the Milky Way from one side to the other at the speed of light would take about 100,000 years. To escape it, even travelling that fast, would take far longer still, because the galaxy's true boundary is not the bright spiral of stars visible in any photograph. It is an invisible sphere of gravity roughly 10 times wider than that disk, built almost entirely from matter that gives off no light of any kind. This is the real physics of leaving the Milky Way, not primarily a rocket problem, but a gravity problem, one that reveals just how large and how tightly bound our own galaxy actually is. What follows traces that gravity outward, from the fastest object humanity has ever launched, to the fastest star nature itself has ever thrown, to the true, almost unimaginably distant edge of the galaxy's pull. The Sun sits about 26,000 light-years from the centre of the Milky Way, roughly 2/3 of the way out along one of the galaxy's spiral arms, in a region so unremarkable that astronomers sometimes call it the galactic suburbs. From here, on a clear dark night, the galaxy itself is visible only as a pale band of light stretching across the sky, the combined glow of hundreds of billions of stars, too faint and too far apart to be picked out one by one. The Sun itself, seen from any real distance beyond the solar system, would look no different, a single pale point of light among billions of others, distinguishable from its neighbours only by its precise position and by the small cold worlds quietly circling it. The spiral arm the Sun occupies is sometimes called the Orion arm, a relatively minor structure compared to the galaxy's two dominant arms, and it is not even continuous, appearing more as a spur or bridge connecting two larger arms than a full arm in its own right. Even the Sun's precise place within the galaxy, in other words, is a modest one, not in a grand spiral arm, not near the crowded centre, but in an unremarkable secondary structure roughly 2/3 of the way to the edge of everything. Nothing in the galaxy is standing still. The Sun and its planets are orbiting the galactic centre at a speed of about 230 kilometers per second, carried along a roughly circular path that takes about 230 million years to complete once, a span of time astronomers sometimes call a galactic year. In that stretch of time, the Sun has circled the galaxy only about 20 times since it formed. Every star visible in the night sky is doing the same thing, held to its own path by the combined gravity of everything else in the galaxy. The stars themselves, the clouds of gas and dust drifting between them, and a far larger quantity of matter that gives off no light at all, and can only be detected by its pull on everything nearby. The Milky Way holds somewhere between 100 billion and 400 billion stars in total, arranged into a flattened disk about 100,000 light-years across. Despite all of that shared gravity, the galaxy is remarkably empty of physical obstacles. The typical distance between neighbouring star systems near the Sun is several light-years, a gap so large that if every star were shrunk to the size of a marble, its nearest neighbour would still sit roughly 1,000 kilometres away. A ship leaving the solar system in almost any direction would not need to dodge anything for a very long time. The difficulty in leaving the Milky Way has never been about collision. It is entirely about gravity, an invisible net cast by every star, every cloud of gas, and every particle of unseen matter in the galaxy, pulling gently but constantly on anything that tries to leave. To leave a gravitational system for good, a traveller does not simply need to move fast. They need to move fast enough that the system's gravity can never quite pull them back, no matter how long it has to try. This threshold is called escape velocity, and it depends only on how much mass is doing the pulling and how far the traveller already is from the centre of that mass. A rocket leaving Earth needs to reach about 11.2 kilometers per second to escape Earth gravity permanently. Move any slower, and gravity eventually wins, either pulling the object back down or settling it into a closed orbit that never truly leaves. The same rule applies at every scale, from a thrown stone to a planet to an entire galaxy. Only the numbers change, and at the scale of a galaxy they change enormously. For an object at the Sun's distance from the galactic centre, astronomers currently estimate the Milky Way's escape velocity at somewhere around 550 kilometers per second. That is roughly 24 times faster than the Sun's own orbital speed around the galaxy, and roughly 50 times faster than the fastest speed any human spacecraft has ever reached relative to the Sun. In more familiar terms, 550 kilometers per second is fast enough to cross the continental United States in about 8 seconds. Sustaining that speed in a straight line, aimed outward from the galaxy rather than around it, is what it would actually take to break free of the Milky Way's gravity from where we sit today. That number comes with a caveat that will matter more and more as the story continues. 550 kilometers per second is the escape velocity from the galaxy, as astronomers currently understand its gravity, and that gravity includes far more mass than the stars and gas that can actually be seen through a telescope. The figure is not calculated from starlight alone. It is inferred from how fast stars orbit at different distances from the galactic center, and those orbital speeds, first measured carefully in the 1970s, did not match what the visible matter alone could explain. Something unseen adds its own gravity to the mix, and that unseen mass turns out to be the single largest factor in how far and how fast anything really has to travel to leave the galaxy behind. No spacecraft built by human beings has ever approached 550 kilometers per second, and nothing currently being designed is expected to either. But nature itself has produced objects that have, flung outward by encounters so violent they make human engineering look almost stationary by comparison, and understanding how they reached that speed begins with the one object humanity has actually sent outward into the dark. Voyager 1 launched from Earth in 1977 and is, by a wide margin, the most distant object humanity has ever sent into space. It crossed the boundary where the Sun's outward stream of charged particles gives way to interstellar space in 2012, and it is still transmitting data back across more than 24 billion kilometers of empty space, a signal that now takes over 22 hours to arrive. Relative to the Sun, it is travelling outward at about 17 kilometers per second, a speed chosen not for its own sake, but because it happened to be the fastest trajectory available after using the gravity of Jupiter and Saturn to gain extra speed on the way out. Voyager 1 is not, strictly speaking, the fastest thing humanity has ever built. That record belongs to the Parker Solar Probe, a spacecraft designed to fly repeatedly through the outer edges of the Sun's atmosphere, which has reached speeds above 190 kilometers per second during its closest passes, roughly 11 times faster than Voyager 1. The difference matters. Parker Solar Probe is fast because it is falling deep into the Sun's own gravity well, and swinging back out again, bound tightly to an orbit that keeps returning it to the same star. Voyager 1 is slower, but it is actually leaving, on a trajectory that will carry it away from the Sun for the rest of its existence. Speed and escape are not the same question, and this distinction between moving fast and actually getting away will come up again and again. Communicating with Voyager 1 today requires the Deep Space Network, a system of large radio dish antennas positioned around the world, so that at least one is always facing the spacecraft as Earth rotates. A single command sent from Earth takes over 22 hours to arrive, and any response takes just as long to return, meaning a simple round-trip exchange, the kind that would take a fraction of a second talking to a satellite in Earth orbit, now takes nearly 2 days. Engineers who work on the mission have described the challenge less as commanding a spacecraft and more as sending a message to a version of the mission that existed almost 2 days earlier, since by the time any command arrives, conditions may already have changed. It is a strange kind of patience, built into the physics of distance itself, and it will only grow stranger as Voyager 1 continues its slow one-way journey outward. At 17 kilometers per second, Voyager 1 would need more than 17,000 years just to cover the distance of a single light year, and the nearest star beyond the Sun, a small red star called Proxima Centauri, sits more than 4 light-years away. Simple arithmetic gives an answer that sounds almost like a joke. At its current speed, Voyager 1 would need roughly 75,000 years to reach that nearest neighbouring star, and it is not even aimed toward it. It is not heading toward any particular star at all. And Proxima Centauri is, by galactic standards, next door. The galactic centre lies about 26,000 light-years away, and the edge of the visible disk lies tens of thousands of light-years beyond that. Set against the 550 km per second threshold estimated for escaping the Milky Way's gravity from the Sun's location, Voyager 1's 17 km per second looks almost trivial, about 3% of what would actually be required. For comparison, 17 km per second is already faster than the speed needed to escape Earth's gravity alone, but Earth's gravity is a rounding error next to the galaxy's. To put that gap in a different frame, matching the galaxy's escape velocity from where we sit would mean travelling faster than a commercial jet by a factor of roughly 1,600. No chemical rocket and no combination of gravity assists available in the solar system could plausibly close a gap that large. Voyager 1 will drift for billions of years, but it will never escape the Milky Way. Long before it could travel far enough, the Sun itself will have changed beyond recognition and Voyager's own power source will have gone silent. Voyager 1 does carry, bolted to its side, a gold-plated phonograph record engraved with sounds and images of Earth, intended for the vanishingly small chance that something, someday, intercepts it. That gesture captures the real proportions of the problem. The spacecraft will spend far longer travelling through the Milky Way than human civilization has existed, and it still will not have gone anywhere at all by galactic standards. It will drift for roughly 40,000 years before passing anywhere near another star, and even then, near does not mean close. It will still be more than a light year and a half from that star at closest approach. Its own nuclear power source, a generator that converts the heat of decaying plutonium into electricity, is expected to fall below the threshold needed to run any instruments sometime in the 2030s. After that, Voyager 1 becomes a silent object, tumbling onward through the dark by momentum alone, carrying no propulsion of its own and needing none, because there is essentially nothing out there to slow it down. If chemistry and gravity assists cannot get anything close to the speed needed, the obvious question becomes whether anything, built or natural, ever has. The answer turns out to be yes, but not through engineering. Deep in the crowded, violent region near the centre of the galaxy, gravity itself has thrown a small number of stars outward at speeds that dwarf anything humanity has built, and the mechanism behind it involves one of the most extreme objects known to exist. At the centre of the Milky Way sits a supermassive black hole called Sagittarius A star, a name inherited from the radio source astronomers first detected there, with a mass around 4 million times that of the Sun, packed into a region not much larger than the orbit of Mercury. A black hole is a region where gravity has become so concentrated that nothing, not even light, can escape once it crosses a boundary called the event horizon. Sagittarius A star does not reach out and grab anything from a distance. Far from its event horizon, its gravity behaves exactly like any other object of the same mass, and stars orbit it the same way planets orbit a star. What makes it unusual is not a suction effect, but the sheer density of mass packed into so small a space, which lets objects passing nearby experience gravitational forces, unlike anything found elsewhere in the galaxy. Occasionally, a pair of stars locked in a close binary orbit wanders too near that black hole. When that happens, the black hole's gravity can rip the pair apart in a process astronomers call the Hills mechanism, named for the astronomer who first worked out the physics in the 1980s. One star in the pair is captured into a tight orbit around the black hole, sometimes settling permanently nearby. Its former companion, robbed of the gravitational partnership that had bound the two stars together, is flung outward in the opposite direction at extraordinary speed, borrowing momentum from the encounter the same way a slingshot borrows momentum from the arm that swings it. The result is what astronomers call a hypervelocity star, and one of the fastest known examples, discovered by a survey named S5 and catalogued as S5 HVS1, is currently moving at roughly 1,755 kilometers per second relative to the galaxy. That is more than 3 times the 550 km per second speed needed to escape the Milky Way from its present location, and more than 100 times faster than Voyager 1. Tracing its motion backward, astronomers found that its path leads directly back to the galactic center, strong evidence that it was ejected by an encounter with Sagittarius A star roughly 5 million years ago, a span of time that sounds enormous but is genuinely brief by the standards of a galaxy around 13 billion years old. The star was found using data from Gaia, a space telescope launched by the European Space Agency in 2013 specifically to measure the positions, distances, and motions of more than 1 billion stars across the galaxy, with extraordinary precision. Without that kind of precise map, distinguishing a star moving at 1,755 kilometers per second from ordinary galactic motion would be far harder. Gaia's measurements are what let astronomers reconstruct the star's path backward through time and connect it to the galactic center with confidence. A speed of 1,755 kilometers per second is difficult to hold in mind using anything from ordinary experience. It is more than 5,000 times faster than a commercial jet, fast enough to cross the distance between the Earth and the Moon in about 3.5 minutes, and fast enough that in the time it takes to read this sentence aloud, the star has already covered a distance greater than the width of several countries, and unlike Voyager 1, S5 HVS1 needed no fuel, no engine, and no decades of careful trajectory planning. Its entire journey was decided in a single, close encounter with a black hole's gravity, a process that took, from the star's perspective, only a matter of hours. Not every hypervelocity star owes its speed to Sagittarius A star. A smaller number are thought to result from a different, equally violent process. A massive star in a tight binary system explodes as a supernova, and the sudden loss of its mass releases its companion from the gravitational bond holding the pair together, flinging that companion outward at speeds of hundreds of kilometers per second, though generally not quite as extreme as the speeds produced by an encounter with the galaxy's central black hole. Distinguishing between the two origins usually comes down to tracing a star's path backward. Stars ejected by the supernova mechanism tend to originate from within the galactic disk itself rather than from the galactic center. Astronomers have now identified several dozen candidate hypervelocity stars, though confirming exactly how fast each one is truly moving and whether its full trajectory really traces back to the galactic center requires careful measurement and is not always certain. Not every fast-moving star qualifies. Many stars move quickly relative to the Sun simply because the Sun itself is moving, and separating a star's true speed from that shared galactic motion takes precise observation. Where the ejection mechanism has been confirmed, though, the evidence is consistent. Only an encounter with the supermassive black hole at the galactic center, or possibly a supernova in a tightly bound binary system, can plausibly explain speeds this extreme. That a natural process near the galactic center can outrun anything human engineering has produced by 2 orders of magnitude says something important about the true difficulty of leaving the Milky Way. It is not primarily an engineering problem, waiting on some future breakthrough in propulsion. It is a problem of gravity so large in scale that only the most violent events in the galaxy, encounters with a black hole millions of times more massive than the Sun, currently manage to send anything past the threshold required. Understanding exactly how large that threshold really is, and why it depends so heavily on something invisible, means looking more closely at what escape velocity actually measures, and where in the galaxy a traveller happens to start. Escape velocity is not one fixed number for the entire Milky Way. It changes depending on where in the galaxy the calculation is made. The rule is straightforward in principle. Escape velocity depends on how much mass lies within the traveller's current distance from the galactic center, and on that distance itself. Move closer to the center, where far more mass is packed into a smaller volume, and the escape velocity climbs sharply. Move farther out, and it drops, though never as quickly as gravity's usual inverse square behavior might suggest, because at greater distances more and more of the galaxy's invisible mass lies enclosed within that larger radius too. Near the galactic center, within a few hundred light-years of Sagittarius A star, escape velocity is estimated at well over 1,000 kilometers per second, a consequence of the enormous density of stars, gas, and the black hole itself, concentrated in that small volume. Out at the Sun's distance, roughly 26,000 light-years from the center, that figure drops to around 550 kilometers per second. Farther out still, at the very edge of the visible stellar disk, current estimates suggest escape velocity falls closer to 300 or 350 kilometers per second, still more than 15 times the Sun's orbital speed around the galaxy, and still far beyond anything a spacecraft could plausibly reach with existing propulsion. If the Milky Way's mass were made up only of stars, gas, and dust, escape velocity would fall off much faster with distance, in roughly the same way that Earth's own escape velocity would be far smaller if measured from the Moon's orbit rather than from the surface. That it does not fall off nearly that quickly is one of the strongest pieces of evidence that most of the galaxy's mass lies not in its visible disk, but in a far larger invisible structure surrounding it, one whose gravity keeps escape velocity stubbornly high across enormous distances, rather than tapering away close to the stars. These figures are not exact in the way a schoolbook constant is exact. Different research teams, using different assumptions about how the galaxy's unseen mass is arranged, have published escape velocity estimates for the Sun's location, ranging from roughly 500 to 550 kilometers per second, and the uncertainty grows larger at greater distances, where direct measurements of orbiting stars become sparser. Astronomers generally treat the higher end of that range as the more likely value, but the honest answer is that the Milky Way has never been weighed with the kind of precision reserved for the mass of the Sun itself. Future missions and longer stretches of Gaia's own survey are expected to narrow this range considerably over the coming decade. Astronomers cannot measure the Milky Way's own rotation curve by watching it from outside the way earlier work observed other spiral galaxies. The Sun sits embedded within the disk itself, looking outward and sideways rather than down on the whole structure from above. Instead, researchers rely on a combination of methods: radio telescopes tracking the faint emission of neutral hydrogen gas at different distances from the galactic center, and, more recently, the extraordinarily precise stellar position and velocity measurements gathered by the Gaia spacecraft, which has tracked the motion of well over 1 billion individual stars, piecing together the Milky Way's own rotation curve from the inside, rather than viewing it from a comfortable outside vantage point the way other galaxies can be studied, is part of why some of these figures remain more uncertain than similar measurements of other, more distantly observed galaxies. A useful way to hold these numbers in mind is to compare them to the fastest object most people will ever personally experience, a commercial airliner cruising at roughly 250 meters per second. Escaping the galaxy from the Sun's location requires a speed about 2,200 times faster than that airliner. Escaping from near the galactic center requires a speed more than 4,000 times faster. Even the outer edge of the visible disk, the most gravitationally forgiving place in the entire galaxy to attempt an escape, still requires a speed over 1,200 times faster than any aircraft has ever flown. Direction matters as well as speed. A star or spacecraft moving at exactly escape velocity, but curving around the galactic center rather than heading straight outward, will not actually leave. Some of its motion is being spent going sideways rather than away. True escape requires enough speed left over in the outward direction alone, after accounting for whatever sideways motion the traveller started with, which is one more reason ordinary orbital mechanics, of the kind that works well for launching satellites around Earth, becomes far less forgiving at galactic scale. Every one of these numbers, whether 300 kilometers per second at the disk's edge or over 1,000 near the center, describes escaping only the part of the galaxy that can be mapped by watching how stars move. Beyond the visible disk lies a region where stars thin out almost entirely, and beyond that, a much larger structure that current models suggest extends for hundreds of thousands of light years, one whose full extent and true edge remain difficult to pin down precisely. Reaching that outer structure and understanding why it changes the whole calculation means first crossing the disk itself and confronting what actually lies in the space between the stars. Reaching 550 kilometers per second, the escape velocity estimated for the Sun's location in the galaxy might sound like a fixed ceiling that engineering simply cannot approach. It is not, in principle. Chemical rockets, the kind that have launched every crewed mission and every probe so far, are limited less by any law of physics than by how much energy can be released from burning fuel and how much of that fuel a rocket has to carry along with it. Every unit of speed gained costs fuel that itself has to be accelerated, a compounding problem engineers call the tyranny of the rocket equation, and it is why no chemical rocket has ever pushed a spacecraft past roughly 20 kilometers per second relative to the Sun without help from a planet's gravity along the way. Ion engines, which accelerate charged particles using electric fields rather than burning chemical fuel, use far less propellant for the same change in speed, but they produce extremely small amounts of thrust, so gaining real speed takes years of continuous firing rather than minutes. NASA's Dawn spacecraft, powered by ion engines, changed its own speed by more than 10 kilometers per second over its mission, an enormous achievement for that technology, but still nowhere near galactic escape velocity. Even the Parker Solar Probe's speed record, over 190 kilometers per second, was achieved not by any engine at all but by repeatedly falling toward the Sun and using its gravity for a boost, a technique that works only because the spacecraft keeps swinging back, bound to an orbit rather than escaping anything. More exotic propulsion concepts, studied seriously by engineers but never built at full scale, suggest that far higher speeds are physically achievable. Project Orion, studied in the 1950s and 1960s, proposed propelling a spacecraft by detonating a sequence of small nuclear explosives behind it, riding the blast waves the way a surfer rides a wave, and calculations at the time suggested speeds of tens of thousands of kilometers per second might be reachable this way, though the concept was abandoned largely over the practical and political problems of deliberately detonating nuclear devices in space. Fusion propulsion, which would draw energy from the same reaction that powers the Sun rather than fission, remains an active area of research, and could in theory reach comparable speeds, though a working fusion rocket engine does not yet exist. A still more exotic concept, antimatter propulsion, would in principle offer even more energy per unit of fuel mass than fusion, since matter and antimatter annihilate each other completely, converting essentially all of their mass into usable energy. No method exists to produce or store more than microscopic quantities of antimatter today, and current manufacturing costs make even a gram of it wildly impractical, so while the physics remains sound in principle, antimatter propulsion belongs, for now, firmly in the category of theoretical possibility, rather than a proposal under active engineering development. The most concrete modern proposal is a light sail, a thin reflective sheet pushed not by fuel at all but by the pressure of light itself. Breakthrough Starshot, a real research program announced in 2016, proposes accelerating a sail only a few meters across, attached to a probe weighing about as much as a smartphone, using a ground-based array of lasers focused on it for a few minutes. Current design targets suggest such a sail could reach roughly 60,000 kilometers per second, about a fifth of the speed of light, and more than 100 times the 550 kilometer per second threshold needed to escape the Milky Way from the Sun's location. No working version of this system has been built, and the engineering challenges, focusing a laser array precisely enough across millions of kilometers, surviving the acceleration, and communicating back across light years afterward, remain unsolved. At 60,000 kilometers per second, a Starshot-class probe would still be traveling at only about a fifth of light speed, a range where the effects of relativity, like time passing slightly slower for the traveler than for observers left behind, are noticeable but modest, nothing like the dramatic time dilation that would appear closer to light speed itself. The nearest star system, Alpha Centauri, sits about 4 1/3 light-years away. A probe genuinely reaching a fifth of light speed could cross that distance in a little over 20 years, a mission length long by any human standard, but not impossible within a single working lifetime. The pattern across every one of these concepts is the same. Reaching galactic escape velocity is not forbidden by physics, but every proposal capable of it applies only to something tiny, a probe weighing grams rather than tons, carrying no crew, no return fuel, and often no way to slow back down once it arrives anywhere. Scaling any of these methods up to something that could carry a human being, or even a substantial scientific payload, multiplies the energy required by staggering amounts, since the energy needed to reach a given speed increases with the mass being accelerated. Current models suggest that a crewed vehicle capable of reaching even a modest fraction of galactic escape velocity remains many decades away at best, and researchers are honest that some version of the engineering problems involved may never be fully solved with technology resembling anything used today. Even setting the propulsion question aside entirely, and imagining a probe that could somehow be built and launched at a speed well past 550 kilometers per second, the space it would then have to cross is not empty in quite the way it might seem from a distance. Between the stars lies a thin but real medium of gas, dust, and radiation, and a probe travelling fast enough to escape the galaxy would need to survive passing through all of it before ever reaching the region where the real barrier, the galaxy's invisible halo, begins. Long before reaching interstellar space proper, any spacecraft leaving the Sun's immediate neighbourhood has to cross the Oort Cloud, a vast, sparse shell of icy bodies loosely bound to the Sun's gravity, thought to extend from roughly 2,000 to as far as 100,000 astronomical units from the Sun, with one astronomical unit equal to the distance between Earth and the Sun. Voyager 1, humanity's most distant spacecraft, has not yet reached even the inner edge of the Oort Cloud, and at its current speed, will not clear the outer edge for something like 30,000 years. Only after that does a traveller genuinely leave the Sun's own gravitational neighbourhood and enter the interstellar medium shared with every other star in the galaxy. Once a hypothetical traveller is moving fast enough to worry about escaping the galaxy, rather than merely orbiting within it, the next question is what actually lies in the way. The space between stars is not empty in the strict sense. It holds a thin distribution of gas and dust called the interstellar medium, along with cosmic rays, magnetic fields, and faint radiation left over from countless stellar explosions over billions of years. But thin is the operative word. A typical patch of interstellar space contains roughly 1 atom per cubic centimetre, compared to about 25 quintillion molecules in the same volume of air at sea level on Earth. By any everyday standard, Interstellar space is about as close to a true vacuum as exists anywhere accessible to a spacecraft. That average conceals real variation. Dense molecular clouds, the regions where new stars are actively forming, can be 1,000,000 times denser than typical interstellar space, though still far thinner than anything that would register as fog or mist to a human observer. A traveller passing through, one would notice essentially nothing by eye, only through instruments sensitive to the faint absorption and scattering of starlight. The solar system itself sits inside a relatively low-density pocket, sometimes called the local bubble, likely carved out by the shock waves of ancient supernovae, one of many such bubbles scattered through the galaxy's disk by the deaths of massive stars over millions of years. The real hazard of crossing the disk is not physical collision with gas or dust, the danger is radiation. Cosmic rays, high-energy particles accelerated by supernova explosions and other violent events, stream through the galaxy in every direction and would pose a genuine risk to any living traveller over a journey lasting years or decades, penetrating spacecraft shielding and biological tissue alike. Within the solar system, the Sun's own magnetic field and the outward stream of charged particles it constantly sheds, together called the heliosphere, provide a measure of natural shielding against the full intensity of interstellar cosmic rays, a bubble of relative protection that extends out to roughly where Voyager 1 crossed into interstellar space in 2012. Beyond that boundary, a traveller loses even that partial shelter and is exposed to the unfiltered radiation environment of the wider galaxy, one shaped by the Milky Way's own weak, large-scale magnetic field, far too faint to protect anything the way the Sun's heliosphere does, but strong enough to influence the paths of the very charged particles it fails to block. This remains one of the genuine unsolved problems for any long-duration crewed mission, and current shielding technology, mostly relying on thick mass to absorb the particles, adds weight that works directly against the goal of reaching higher speeds in the first place. The Milky Way's visible disk is roughly 100,000 light-years across, though the distance actually facing a traveller leaving from the Sun's position out toward the disk's edge is closer to 25,000 light-years. At the speed of light, itself unreachable for any physical object with mass, that distance alone would take 25,000 years to cross. At the 550 km per second escape velocity from the Sun's location, the same distance would take roughly 13.6 million years. At Voyager 1's 17 km per second, it would take longer than the current age of the universe several times over. These numbers describe only the disk, the innermost and smallest of the three regions a true escape has to pass through. Beyond the disk's edge, the density of stars falls away quickly. Rather than a hard boundary, the transition is gradual. The crowded spiral arms give way to a much sparser scattering of stars, thinning out over tens of thousands of light-years, until individual stars are separated by distances that make even the solar neighbourhood look crowded by comparison. This thinning marks the start of what astronomers call the Galactic halo, a region defined less by what can be seen there, which is very little, and more by what its gravity implies must be there, largely unseen. Crossing the disk, in other words, is mostly a matter of surviving a very long, very sparse journey, with radiation as the real danger rather than any physical barrier. What waits immediately beyond it is a different kind of region entirely, a faint scattering of some of the oldest stars in the galaxy, and clusters of stars far older than the Sun, marking the last visible landmarks before the galaxy's gravity becomes almost entirely a matter of things that cannot be seen at all. Past the edge of the crowded spiral disk lies a region astronomers call the stellar halo, a roughly spherical, extremely sparse population of stars surrounding the galaxy in every direction, rather than confined to a flattened plane. These stars are, on average, far older than the Sun and far poorer in heavier elements, chemical fingerprints suggesting many of them formed before the galaxy had built up much of its later generations of stars, or were captured from smaller galaxies that the Milky Way absorbed over billions of years of its history. Scattered through the stellar halo are roughly 150 known globular clusters, each a tightly packed, roughly spherical ball containing anywhere from tens of thousands to more than 1,000,000 stars, held together by their own mutual gravity, orbiting the galactic center on paths that carry some amount to 300,000 light-years or more, 3 times the width of the visible disk. Globular clusters are among the oldest structures in the galaxy, with ages for the oldest examples estimated at close to 13 billion years, nearly as old as the universe itself. A traveller crossing the outer stellar halo would pass, At most, a handful of these distant ancient clusters, each a faint, dense knot of starlight against an otherwise nearly empty sky. One of the largest known globular clusters, Omega Centauri, contains an estimated 10 million stars packed into a sphere roughly 150 light-years across, dense enough that some astronomers suspect it may be the stripped-down core of a small galaxy the Milky Way absorbed and disassembled long ago, rather than a globular cluster that formed the ordinary way. Structures like it blur the line between a star cluster and the remnant of an entire small galaxy, and studying them has become one of the main ways astronomers reconstruct the Milky Way's long history of growth by consuming its smaller neighbours. Some of the stars in the outer halo did not form in the Milky Way at all. Over billions of years, the Milky Way has gravitationally captured and slowly torn apart a number of smaller, satellite galaxies that wandered too close, stretching their stars into long, thin trails called tidal streams that can still be traced today, stitched across large portions of the sky. The Sagittarius dwarf galaxy, currently in the process of being absorbed, has left one of the most prominent such streams, a ribbon of stars looping around the Milky Way that current models suggest has already made several full passes. The outer halo, in this sense, is partly a graveyard of smaller galaxies the Milky Way has consumed. Distances to globular clusters are measured using a class of pulsating stars called RR Lyrae variables, whose brightness rises and falls on a predictable schedule, tied directly to their true luminosity, allowing astronomers to work out how far away they must be, simply by comparing how bright they appear from Earth to how bright they actually are. This technique, refined over more than a century of observation, is one of the fundamental tools used to map distances not just within the Milky Way's halo, but across much of the observable universe. The stars that make up the stellar halo and its globular clusters are also markedly poorer in heavy elements than the Sun. A chemical signature astronomers call metal poverty, using the word metal loosely to include almost anything heavier than hydrogen and helium. That poverty reflects their age. They formed early in the galaxy's history, before generations of exploding stars had enriched the surrounding gas with the heavier elements that later stars, including the Sun, would go on to incorporate. Density in the outer halo is almost impossible to convey through numbers that mean anything intuitively. Where the solar neighbourhood has a handful of stars within a few light-years, the outer stellar halo has, on average, roughly one star for every hundreds of thousands of cubic light-years of space. A traveller moving through it at even the fastest speeds achievable by any known method would likely pass an entire human lifetime without a single star coming close enough to be visually distinguished from a faint background point of light, and might never come within even 100 light-years of one at all. At these distances, escape velocity has already dropped from the 550 km per second measured near the Sun to something closer to 300 km per second, a consequence of how much less enclosed mass appears to lie within a sphere this size, at least based on the visible stars and gas alone. That the number has not dropped further, given how little visible matter remains out here, is itself a clue that something else, something that gives off no light, is still contributing significant gravity at these enormous distances. The stellar halo is the last part of the Milky Way that can be mapped primarily by counting visible stars. Beyond it, at distances the outer globular clusters only begin to sample, lies the structure that actually determines whether anything ever truly escapes the galaxy. An enormous, invisible halo of matter, inferred entirely from its gravitational effects, whose extent dwarfs everything encountered up to this point combined. Understanding what that matter actually is, and how astronomers came to realize it was there at all, changes the entire scale of the problem of ever truly leaving the galaxy. Every layer of the Milky Way encountered up to this point, the disk, the stellar halo, the globular clusters, can be mapped by observing light. Starlight, the glow of gas clouds, the faint signatures of chemical elements. The structure that actually dominates the galaxy's gravity, and therefore its escape velocity, gives off no light of any kind and cannot be observed directly by any telescope built to date. Astronomers call it dark matter, a name that describes what it does not do rather than what it is. The case for its existence rests on one of the most carefully confirmed observations in modern astronomy. In the 1970s, the astronomer Vera Rubin, working with colleague Kent Ford, measured how fast stars orbit at different distances from the centers of spiral galaxies, including the Milky Way's neighbors. Basic physics predicts that stars far from a galaxy's center, where less visible mass lies enclosed within their orbit, should move more slowly than stars closer in, the same way outer planets in the solar system orbit the Sun more slowly than Mercury does. Rubin and Ford found instead that orbital speeds stayed roughly flat, barely dropping at all even far out into a galaxy's faint outer reaches, a result now called the flat rotation curve, and one that has since been confirmed in hundreds of other galaxies. The only way to explain a flat rotation curve using known physics is if far more mass is present than the visible stars and gas can account for, spread out through a much larger volume than the visible galaxy occupies. That additional mass, astronomers concluded, must exist as some form of matter that interacts with gravity normally but does not emit, absorb, or scatter light in any way that current instruments can detect. Estimates suggest dark matter makes up roughly 85% of all the matter in the universe, with the ordinary matter that makes up stars, planets, and everything visible accounting for the remainder. This conclusion is reinforced by an entirely independent line of evidence: gravitational lensing, the bending of light from distant background galaxies as it passes near a massive foreground object, predicted by Einstein's general theory of relativity. Maps of how light bends around galaxy clusters consistently show far more bending than the visible matter in those clusters could produce on its own, requiring the same additional unseen mass that flat rotation curves imply. Two independent methods, measuring orbital speeds and measuring bent light, arriving at the same conclusion, is a large part of why the existence of dark matter, whatever its ultimate nature, is treated as well-established physics rather than a speculative guess. Within the Milky Way, this dark matter is thought to form a roughly spherical halo enveloping the entire visible galaxy, extending far beyond the outermost globular clusters. Estimates of its true size vary considerably between different research teams and different methods of measurement, but current models generally place its outer edge somewhere between 300,000 and 600,000 light-years from the galactic center, several times wider than the visible disk. The evidence suggesting the halo has an outer edge at all comes mainly from studying the faint motion of distant satellite galaxies and streams of stars torn from smaller galaxies, rather than from any direct detection, so the true boundary, if a boundary in the ordinary sense exists at all, remains one of the least certain numbers in this entire reckoning of the galaxy's gravity. What dark matter actually consists of remains one of the most significant open questions in physics. Leading candidates include hypothetical particles that interact with ordinary matter only through gravity and possibly the weak nuclear force, and a number of dedicated experiments buried deep underground to shield them from other radiation have spent decades searching for a direct detection without success so far. Dedicated detectors such as the Xenon experiment, buried nearly 1.5 miles underground in an Italian mountain laboratory to shield it from cosmic rays and other interference, have spent years watching for the extraordinarily rare signal a dark matter particle might leave behind if it happened to collide with an ordinary atomic nucleus. So far, none of these experiments have produced a confirmed detection, a result that has itself narrowed the range of properties dark matter particles could plausibly have, even as it leaves the fundamental question of what dark matter actually is unresolved. Some researchers have proposed alternative explanations that modify the equations of gravity itself rather than adding unseen mass, though the current evidence, drawn from many independent lines including gravitational lensing and the detailed structure of the cosmic microwave background, is generally considered to favor the existence of genuine unseen matter over a modification of gravity's basic laws. Whatever it ultimately turns out to be, the dark matter halo is estimated to outweigh every star, every planet, and every cloud of gas in the visible Milky Way combined by a factor of roughly 5 to 1. It is, in the most literal sense, the majority of the galaxy, and it is the reason escape velocity from the Milky Way does not drop off the way it would from the visible disk alone. Understanding exactly how far its gravity actually reaches, and what escaping it would truly require, means confronting the largest and least certain number in this entire journey. Combining every layer of gravity traced up to this point, the full picture of what it would take to leave the Milky Way looks considerably larger than the 550 km per second figure that describes only the Sun's position within the visible disk. Because the dark matter halo extends so far beyond the stars, escape velocity does not fall away quickly with distance the way it would around an object like a planet or an ordinary star. At 100,000 light-years from the galactic center, well beyond the visible disk, and well into the dark matter halo, Current models suggest escape velocity may still be somewhere in the range of 400 kilometers per second. At 200,000 light-years, more than twice the width of the entire visible galaxy, it may still be several hundred kilometers per second, only gradually approaching a much lower figure as a traveller nears the halo's outermost, least certain edge. Estimates of the Milky Way's total mass, dark matter included, have grown substantially over the decades as observational techniques improved. Early 20th century estimates based only on visible starlight suggested a total mass a small fraction of what is now accepted. Current estimates, incorporating the orbits of distant satellite galaxies and precise stellar motion data from missions like Gaia, place the Milky Way's total mass, including its dark matter halo, at somewhere between 700 billion to 2 trillion times the mass of the Sun, an enormous range that itself reflects how difficult this measurement remains. There is no wall to cross, no clean boundary where a traveller could look back and say the galaxy has been left behind. Gravity has no edge in the way a coastline has an edge. It simply grows weaker and weaker with distance, in principle never reaching exactly zero. What astronomers mean by escaping the Milky Way is a traveller's total energy becoming positive, moving fast enough, given how much speed the galaxy's gravity has already stolen along the way, that the traveller will keep receding forever rather than eventually slowing to a stop and falling back. It is a mathematical threshold, not a physical location, and by that definition, the region where escape becomes assured stretches across hundreds of thousands of light-years, not a single line. Much of what astronomers know about the outer reaches of the dark matter halo comes from studying the motion of the Milky Way's own satellite galaxies, particularly the Large Magellanic Cloud, a smaller galaxy roughly 160,000 light-years away, visible to the unaided eye from the southern hemisphere as a hazy patch resembling a detached piece of the Milky Way itself, precisely measuring how fast the Large Magellanic Cloud is moving, and comparing that speed to how tightly the Milky Way's gravity should be holding it at that distance, gives astronomers one of their best direct constraints on how much mass the halo actually contains far from the visible disk, a method that has led to some of the more recent and higher mass estimates for the galaxy as a whole. Even S5HVS1, the hypervelocity star ejected by an encounter near the galactic center, moving at roughly 1,755 km per second, comfortably above every escape velocity estimate given for the Sun's neighborhood, or the halo beyond it, would still need a very long time to actually put the halo behind it. At that speed, crossing 300,000 light-years, a reasonable estimate of the halo's radius, would take a little over 51 million years. That is genuinely fast compared to anything humanity has built, and genuinely truly slow compared to how long the halo itself is wide. 51 million years is difficult to place against anything in ordinary experience, but a comparison helps. It is roughly the amount of time that has passed since a large asteroid struck Earth and ended the age of the dinosaurs, doubled and then doubled again, and then added to once more. A star ejected from the galactic center around the time the earliest primates were evolving on Earth would only now, after all of recorded human history, and the entire span of human evolution before it many times over, be approaching the outer edge of the halo it needs to cross. It is worth being honest about how uncertain the outer boundary of the halo really is, because the evidence comes almost entirely from the motion of a small number of distant satellite galaxies and faint stellar streams, rather than from direct measurement of the dark matter itself. Different studies have produced halo mass and radius estimates that disagree by a factor of 2 or more. Some researchers argue the halo may extend even farther than the commonly cited range, blending gradually into the surrounding cosmic web of matter that connects every galaxy to its neighbours, rather than ending at any definable point at all. Whatever its precise outer limit, the dark matter halo is, by a wide margin, the largest and most gravitationally significant structure surrounding the Milky Way, dwarfing the visible galaxy that gives it its name and its familiar spiral shape. Once a traveller, or a star, has genuinely put that halo behind it, what remains is not another layer of the Milky Way at all, but the space between galaxies themselves, and an entirely different kind of view. Suppose, for the sake of the thought experiment, that a traveller somehow crossed the entire dark matter halo and genuinely left the Milky Way's gravity behind. What would actually be out there is mostly more of the same. Darkness punctuated by faint distant points of light, each one an entire galaxy rather than an entire star. The Milky Way does not exist alone. It belongs to a collection of roughly 80 known galaxies, large and small, called the local group, bound loosely together by their mutual gravity across a region of space roughly 10 million light-years across. The largest galaxy in the local group besides the Milky Way is Andromeda, a spiral galaxy similar in overall shape and somewhat larger in size, sitting about 2.5 million light-years away. Light from Andromeda takes 2.5 million years to reach Earth, meaning the galaxy as seen tonight shows how it looked well before modern humans existed. From a vantage point well outside the Milky Way, having crossed its dark matter halo, Andromeda would already have been visible for most of the journey, as it is even from Earth, a faint elongated smudge of light in a clear dark sky, the most distant object visible to the unaided human eye. From outside the Milky Way's own halo, however, the Milky Way itself would begin to look the same way. Andromeda always has looked from here, a distant, glowing disk of light, one galaxy among many, rather than a home. This is the final version of an image that has recurred again and again at ever greater distance. The Sun, once described as a single pale point of light among billions of others, as seen from beyond the solar system, would from this vantage point not even be individually visible. The entire Milky Way, all 100 billion to 400 billion of its stars, including the Sun, would blur into a single softly glowing shape, indistinguishable in kind from any of the dozens of other galaxies scattered through the surrounding darkness of the local group. The space between galaxies, sometimes called intergalactic space, is even emptier than the space between stars within a galaxy. Average densities there are estimated at roughly 1 atom for every few cubic meters, compared to roughly 1 atom per cubic centimeter within the Milky Way's own disk, a difference of many orders of magnitude. A traveller genuinely out in that space would see almost nothing nearby at all. No stars close enough to distinguish individually, no clouds of gas bright enough to notice, only the distant, unmoving glow of entire galaxies scattered unevenly across the sky, some in loose clusters, most simply alone. Some intergalactic space is not entirely empty even beyond the reach of any single galaxy's halo. A diffuse, extremely hot gas called the intergalactic medium, and filamentary structures known as the cosmic web, connect galaxies and clusters of galaxies across billions of light-years, themselves shaped by the gravity of dark matter on the largest scales astronomers can observe. Beyond Andromeda, the local group includes dozens of far smaller galaxies, most too faint to see without a telescope, among them the Triangulum galaxy, a modest spiral about 2.7 million light-years away, and a scattering of dwarf galaxies containing anywhere from a few million to a few hundred million stars each, orbiting the Milky Way or Andromeda much as moons orbit a planet. From well outside the Milky Way's own halo, a hypothetical observer would see this whole loose family laid out at once. Two large spiral disks, the Milky Way and Andromeda, drawing steadily closer to one another, and a scattering of far smaller, fainter companions arranged around them. The entire local group occupying a volume of space that, despite containing dozens of galaxies, remains overwhelmingly empty by any ordinary standard of the word. Everything within the local group is gravitationally bound to everything else in it, meaning that unlike more distant galaxies, which the overall expansion of the universe is slowly carrying farther away, the Milky Way, Andromeda, and their smaller neighbours are not simply drifting apart. Their mutual gravity, dominated once again mostly by dark matter, has already begun overcoming that expansion, at this comparatively close range, on a trajectory that current models suggest will eventually bring some of these galaxies together entirely. Andromeda, in particular, is not standing still relative to the Milky Way. It is approaching, and current measurements of its motion give astronomers a reasonably confident picture of what that approach eventually leads to, on a timescale that dwarfs even the tens of millions of years already discussed for crossing the halo. Andromeda's motion toward the Milky Way was first measured through a shift in the colour of its light, a technique that can determine whether a distant object is moving toward or away from an observer, and by how much. That measurement shows Andromeda closing the distance at roughly 110 kilometers per second. Combined with more recent measurements of Andromeda's sideways motion, astronomers now believe the two galaxies are on a course that will bring them together, rather than simply passing at a safe distance, though the exact timing and details of that encounter depend on assumptions about both galaxies' total mass, including their dark matter halos, that carry real uncertainty. Current models place the beginning of the collision at roughly 4 to 5 billion years from now, a span of time longer than the Sun has existed so far. The word collision is doing more work here than it might suggest. Because individual stars are separated by such enormous distances, direct collisions between stars during the merger are expected to be exceedingly rare, essentially negligible even as the two galaxies pass through each other. What actually happens is a slow, repeated gravitational dance. The two galaxies will likely pass through one another, swing back under their mutual gravity, and pass through again several times over roughly 2 billion years, each pass distorting both galaxies' shapes, flinging some stars, possibly including the Sun, onto entirely new orbits far from where they started. Astronomers do not have to rely on simulation alone to know roughly what a galaxy merger looks like. The universe is full of galaxies caught in the act, at every stage of the process. The antennae galaxies, a well-studied pair roughly 60 million light-years from Earth, show exactly the kind of distorted spiral arms, long streaming tails of stars, and bursts of new star formation that models predict for the Milky Way and Andromeda's eventual encounter, offering a real observed preview of a process our own galaxy has not yet begun. Comparing dozens of such systems at different stages, some just beginning to interact, and others nearly finished merging into a single elliptical shape, is how astronomers built the confidence behind the multi-billion-year timeline described for our own galaxy's future. While stars themselves mostly pass by each other undisturbed, the vast clouds of gas within each galaxy do collide, and that collision is expected to trigger a significant burst of new star formation, compressing gas clouds and igniting the birth of large numbers of new stars over a relatively short span of a few 100 million years, a brief and intense episode compared to the billions of years the merger itself will take. Eventually, the two spiral galaxies are expected to settle into a single, larger elliptical galaxy, a smoother, rounder shape without the pinwheel arms either galaxy has today, sometimes informally nicknamed Milkomeda, by astronomers discussing the merger, though that name has no official standing. This would not be the Milky Way's first merger. The tidal streams and unusual globular clusters described earlier, including the remnants of the Sagittarius dwarf galaxy, and a larger ancient merger with a galaxy astronomers have named Gaia Enceladus, suggest the Milky Way has absorbed a number of smaller galaxies over the past 8 to 10 billion years, gradually growing to its current size and mass. Meeting Andromeda would be, by a wide margin, the largest such merger in the Milky Way's history, but not a fundamentally new kind of event for a galaxy that has spent billions of years slowly consuming its smaller neighbours. What happens to the solar system specifically during all of this remains genuinely uncertain. Current simulations suggest the Sun, by then likely already in the later stages of its own life, has a reasonable chance of being flung onto a new orbit within the merged galaxy, farther from the galactic centre than its current position, though a small chance also exists that it could be ejected from the merged galaxy entirely, becoming in effect its own kind of hypervelocity traveller, cast outward not by a black hole encounter but by the combined chaos of an entire galactic merger. This same physical mechanism, gravitational disruption during a close pass between massive systems, is thought to be responsible for producing some of the hypervelocity stars observed racing through other galaxies today. Beyond the local group, an entirely different force is at work, one that has nothing to do with any individual galaxy's gravity. The universe as a whole is expanding, and that expansion is accelerating, driven by something cosmologists call dark energy, a term that, much like dark matter, names an observed effect rather than a fully understood cause. Galaxies far beyond the local group's gravitational reach are steadily receding from the Milky Way, and the more distant a galaxy is, the faster it appears to be moving away. Given enough time, current models suggest that most galaxies beyond the local group will eventually recede faster than light could ever cross the growing distance between them, passing permanently beyond any possibility of contact, a boundary cosmologists call the cosmic horizon. In an important sense, then, most of the universe is already escaping the Milky Way far more effectively and far more permanently than the Milky Way's own gravity could ever be escaped from the inside. The one honest exception, gravitationally bound and drawing steadily closer rather than farther, is the neighbour just described, Andromeda. Add together Voyager 1's patient glacial crawl outward, the violent gravitational slingshot that flung S5 HVS1 past the galaxy's escape threshold in a matter of hours, and the vast, invisible dark matter halo that makes that threshold so much larger and so much farther reaching than the visible galaxy alone would suggest. And one conclusion holds firm. Nothing humanity has ever built has come remotely close to escaping the Milky Way, and nothing currently being designed is expected to either. The obstacle has never really been engineering in the way that phrase usually gets used. Chemical rockets, ion engines, gravity assists, even the most exotic light sail concepts studied to date all face the same underlying arithmetic. Escaping a gravitational system this large, wrapped in a halo of matter that outweighs every visible star combined, requires speeds that dwarf anything a spacecraft carrying real mass, real instruments, or a human crew has ever achieved. The barrier is gravity itself, operating at a scale that makes the entire solar system, and every rocket ever launched from it, look small by comparison. Only nature's most violent gravitational events, close encounters with the supermassive black hole at the galactic center, have managed to send anything decisively past the escape threshold, and even they remain rare. Of the several dozen credible hypervelocity stars astronomers have identified to date, each one required a chance encounter with Sagittarius A star that most stars in the galaxy, including the Sun, will never experience. Even those fortunate few, moving at speeds that make Voyager 1 look stationary, still need tens of millions of years just to clear the galaxy's dark matter halo, a span of time so much larger than any length of human history that it resists easy comparison. The Milky Way holds somewhere between 100 billion and 400 billion stars in total, and only a few dozen confirmed hypervelocity stars have ever been identified among them, a fraction so small it barely registers against the whole population. Nearly every star in the galaxy, including the Sun, will spend its entire existence gravitationally bound, orbiting the same galactic center, never once approaching the speed such an escape would require. None of this means the Milky Way should be thought of as a cage. Every star in this picture, the Sun included, orbits the galactic center on a stable, predictable path that has held for billions of years, and will hold for billions more, long enough that the entire question of escape has always been closer to a thought experiment than a practical concern for anything alive today. The same gravity that makes escaping so difficult is the gravity holding the Sun, the Earth, and every other star in a comprehensible, orderly structure rather than a chaotic scatter of drifting bodies. What all of this really shows is not a travel plan but a measurement, just how large the Milky Way genuinely is. Once its full gravity, most of it invisible, is properly weighed. The bright spiral disk visible in any photograph, the part most people picture when they hear the word galaxy, turns out to be only the innermost, smallest layer of something many times larger, wrapped in a halo of matter that cannot be seen, but can be weighed, measured, and however imperfectly understood. Escaping it was never really the point of asking the question. The point was discovering how much of the galaxy was never visible to begin with. The Sun continues its slow circuit around the galactic center, one lap roughly every 230 million years, carrying Earth and everything on it along a path bound by gravity, reaching out across hundreds of thousands of light years in every direction, most of it made of something that has never once been seen, only felt in the quiet, patient bending of every orbit it touches. Voyager 1, still drifting outward at 17 kilometers per second, will keep transmitting for only a few more years before its power finally runs out, becoming a silent, drifting object that will nonetheless keep moving through the galaxy for billions of years afterward, carried along by nothing but the momentum it already has. It will never catch up to the speeds nature achieves through violence, and it was never trying to. It was only ever meant to look closely at a few nearby worlds and then keep going, a small, human-built object continuing an outward drift that the Sun itself has been making, at a far larger scale for the entirety of its existence, around a galactic center bound by gravity that reaches out unseen for hundreds of thousands of light years in every direction. Somewhere out past the edge of the visible Milky Way, farther than the last globular cluster, farther than the faintest stellar stream torn from some smaller galaxy consumed long ago, the galaxy's gravity is still there, thinning slowly across hundreds of thousands of light years, made almost entirely of a substance that has never been touched, tasted, or seen directly, only inferred from the way it bends the paths of everything around it. That is the real shape of what leaving the Milky Way actually requires. Escaping the Milky Way was never simply a matter of engines and fuel. Every proposal capable of reaching the necessary speed applies only to something small, and even the fastest natural object ever measured, flung outward by an encounter with a black hole, needs tens of millions of years to actually put that gravity behind it. For now, and for the whole of any recognizable human future, The Sun and everything orbiting it remain exactly where gravity has always kept them, one star circling one galactic center, bound to a structure so much larger than its own bright disk that the visible Milky Way turns out to be only a small, luminous fraction of something far vaster and far darker than it first appears.